right, we're starting our discussion of biological molecules and talking about water and the aqueous environment. So we talked about the physical and the chemical characteristics of water. And then, just to tie everything up, we just say, well, these are some specific ways that macromolecules, so many of the biological molecules are macromolecules like DNA and protein. These are some of the ways that they act in aqueous systems. So we started out just talking about some real sort of simple, straightforward things that, like common sense that, if you have two DNA molecules that are surrounded by negative charge with a phosphate backbone on now try to ionize, that they're going to repel each other. They're going to want to stay away from each other. And similarly, if you have a protein that's negatively charged, they're going to repel each other. Or two proteins that are positively charged will repel each other. But if you have a positive-negative interaction, then they're going to attract each other. And sort of the example of that is if you have negatively charged DNA and positively charged histones, we're going to talk about this in detail in a week or so, that those actually then will attract each other. They make stable complexes. That's all to be pretty simple. Now, one thing, the final point I basically want to talk about is to talk about proteins and the effect of pH on the charge in proteins, and then ultimately the solubility. So I think this is what's in my this is like point number 3 I have under macromolecular interactions. And the charge of macromolecules, in particular proteins, depends upon pH. To kind of show how that works, right now we're just going to have our protein be a big blob. We're going to get into all the detail later of that. But here's our big blob. And then proteins are made up of amino acids. We're going to get into this in a lot of detail. And they have side chains. The functional groups coming off the side chain tend to be carboxyl groups. And there are a lot of amino groups. Carboxyl groups from side chains like glutamate and aspartate, and amino groups with lysine. And typically, what do we say? The pKa of a carboxyl group is 2 to 4. pKa of an amino group, what do we say, 9 or 10? So that at pH 7, you tend to have the carboxyl groups tend to be deprotonated, so they have a negative charge. And the amino groups tend to be protonated. But if you go down to a low pH, now we're going to have our protein here. And at a very low pH, then we're going to start protonating some of our carboxyl groups. But the amino groups are going to continue to be protonated. So this is at low pH, proteins tend to have a positive charge. And then similarly, if we have here's our protein blob here. If we go to a high pH, the carboxyl groups remain deprotonated. Let me do this like this. Where at high pH, these amino groups begin to get deprotonated. pH, they tend to have a negative charge. Now, the exact pH at which you have a neutral charge is really going to depend upon the specific protein. I just kind of put a generic one in that it kind of has equal amounts of carboxyl groups and amino groups. But some proteins are more acidic, means they have a lot more carboxyl groups than amino groups, okay? And some proteins are more basic, meaning that they have a lot more amino groups than carboxyl groups. So depending upon the relative balance of amino groups and carboxyl groups, the pH at which you actually end up being neutral is going to differ. And the pH at which it is neutral is known as the isoelectric point. Also known as the pI, which is the pH at which there is no net charge. And that pI is going to differ between different proteins depending upon the amount of amino groups and carboxyl groups. And there's some other ionizable side chains of proteins, thiols and phenols and that sort of stuff that I haven't, for the sake of simplicity, I haven't necessarily thrown in there. That also influence. So depending upon the amino acid composition of the protein, different proteins will have different pI. Now, what the final point I might make about the point is at the isoelectric point I, the pH at which there's no net charge, and it also tends to be when proteins often aggregate, come out of solution. And they aggregate because you've got areas of both positive and negative charge on the surface of your protein. And so here's another protein molecule with a positive charge will start interacting with the negative charge, and then the negative charge in it will interact with a positive charge as part of another protein. You'll basically get them all they'll all tend to form a big mass. Whereas at low pH, where they all have a positive charge, they're repelling each other. At high pH, where they all have a negative charge, they're repelling each other. But at the pI, where they have this mixture of positive and negative charges, the areas can actually combine and interact. Now, the final point I'm going to make, and then I'm going to bring up a few slides that are actually from your textbook, just to kind of do a better job of drawing, basically, and illustrate this point. The final point that I want to make here is that the interaction between molecules can be shielded by small ions. That is the ionic strength high ionic strength reduces interactions between the molecules. because basically if you have, say, sodium chloride, real simple salt, it could be potassium chloride, sodium chloride, but say sodium chloride, your sodium ions will begin interacting with the carboxyl group, and the chloride ions will interact with the amino groups, and that will basically shield those charges so the proteins no longer interact with each other. They're interacting with the small ions instead. All right, let me go ahead and bring down. All right, so this is a figure from your text, basically looking at the effect of pH here on the charge of the molecule. And so this is your blob of a protein, and the blue areas are the areas, say, where there's a high concentration of amino groups. Those are the basic areas. That's the positively charged areas. And so as you go at lower and lower pH, you get more areas that have a positive charge. And then as you get higher and higher pH, as those carboxyl groups become deprotonate and ionized, you get very high pH, then it basically all turns negative. So again, low pH tends to be positive, high pH tends to be negative, and then at this isoelectric point in here, you've got areas of both positive and negative charge. So what happens when you have that area of both positive, negative charge, this is another example here. This is going to be at high pH where you have a whole bunch of negative charge. Then lower pH, you basically have these areas of positive, negative charge, and then ultimately those things can then start interacting with each other, and you get these things to actually aggregate in solution. This is often an issue. That's the higher pH. So if you look at solubility, okay, relative to pH, the lowest solubility for a protein is going to be right near its pI. Whatever pH is, F, the maximum amount of both positive and negative charges from here. And then this is another figure that just illustrates that shielding effect. That basically, under low ionic strength, when you have these positive and negative interactions here, the macromolecules can interact. But as you start having a high ionic strength, represented by these little blue and red dots from, say, sodium chloride or something like that, they'll basically interact and kill the molecules and prevent them from interacting together. All right. That sort of wraps up our discussion of water. And then we go, from your text standpoint, we skip over the thermodynamics. We're going to come back at the very beginning of next semester and review thermodynamics before we get into metabolism. And but in the meanwhile, we're going to go ahead and first start with our first, biological molecule that actually has carbon in it. We're going to start with the nucleotides. You'll see different texts organize things a different way. A lot of the classic way is to start with amino acids and build up proteins, and then do nucleic acids after you do sugars. But for some textbooks, you like this one, it works pretty well. Sort of follow, in a sense, the central dogma of biology, basically saying, okay, we've got DNA encodes RNA, and then the RNA then encodes the protein, and have that sort of central dogma. So before we talk about proteins, we're talking about the nucleic acids, DNA and RNA. Now, before we can talk about those nucleic acids, we're going to have to talk about the small molecules that actually those nucleic acids are built up of. And so we're going to start by talking about the nucleotides. So this whole chapter is nucleotides, nucleic acids, Well, we're first going to talk about nucleotides. A nucleotide consists of a base plus a sugar plus a phosphate. We're going to focus on the base. Now, by now, most of you guys probably had a year of biology, or you might be finishing up a second semester of biology and everything. And so you've seen this DNA, AT, GC, and all that sort of stuff. And so some of this might actually be a little bit of a review for you. Except what we're really going to try to do is really focus more on the chemistry, to sort of no longer start talking about it just about letters, connected by lines, but actually start looking at the molecules and the characteristics of the molecules. Okay, so we're going to first talk about our bases. And there are two structural classes. And the first one, we're going to talk about the pyrimidines. And pyrimidines have this basic, this is pyrimidine here. That's a pyrimidine. But what we're going to do is we're going to derivatize that to actually make the bases that are used in nucleic acids. First one we'll start out with is cytosine. And one of the things that one of the things that I want to emphasize here is the chemistry in terms of its ability to form hydrogen bonds. Because what we're going to see is hydrogen bonds are very important in the base pairing aspect of DNA structure. And so as I'm writing this structure of the base, what I want to do is that we basically show that we've got these two unpaired electrons. So this can be an H bond recipient. That means, we've got a partial negative charge here that can interact with a partially positive charged hydrogen. This is a hydrogen bond recipient here, that lone pair, where here is an H bond donor. Now let's talk about cytosine, or thymine. recipient. Here's a potential H bond donor. Here's an H bond recipient. Up here. And while I've got them up here, I'm just going to go ahead and write side by side uracil. We do the same thing as thymine, except no methyl group. Now, when we start building the nucleotides and making the nucleic acids, which nucleic acid uses uracil rather than thymine? RNA, right? So this is an RNA, whereas this is in DNA. Now, the good question is why? Why does RNA have uracil while DNA has thymine? What is it about that methyl group that makes this better for things? There's really two reasons. So, if we ask why thymine in DNA, one reason is there's more, when you actually get into the helix, there's more conformational flexibility in here, and so this can end up base pairing more easily with other, we'll talk about base pairing a little bit, but thymine normally base pairs with adenine. Uracil base pairs with adenine, but it also base pairs with certain frequencies with some other things, so there's less fidelity. So the first reason is higher fidelity base pairing with adenine. The other thing you have to think about, DNA molecule is a relatively long-term information storage molecule, right? We have to keep the DNA around for a long time, make it used both for transcription and ultimately replicated. So it's the long-term storage molecule. Whereas RNA, it's a relatively short-term molecule, whether it's as mRNA, where it just, it gets made in response to transcription, and then it gets has a brief lifetime where it carries the information to the ribosome for protein synthesis, or if it's a tRNA, it's just used briefly to relate the mRNA to a particular amino acid. It's short-term information molecule. So you need basically a higher fidelity and a higher fidelity and greater stability for the DNA molecule relative to the RNA molecule. So the second reason is when cytosine, one of the things that happens to cytosine in a DNA molecule, just because of chemical breakdown kind of thing, is you can get deamination. So deamination of cytosine makes uracil. So if this amino group comes off, you transfer the amino group to a keto group, you end up making uracil. Okay. Now there are enzymes that go and repair those fixes. Okay? Well, if you have now a DNA molecule that has both uracil that's supposed to be there for coding reasons, as well as uracil that got there because it got deaminated from cytosine, those repair enzymes can't differentiate between the uracil that's supposed to be there and the uracil that that got there because of this deamination of cytosine. So, so by having this methyl group, having this group here, it differentiates between the coding molecule, which is now thymine, and the molecule, the degradation product of cytosine. So it basically, the other reason is it differentiates cytosine degradation product, uracil, from the coding thymine. So that a repair enzyme can basically cleave out all the uracils that's fine, replaces them with cytosine and fixes things without having danger of actually changing the coding. All right. Now, drawing the structures, one of the things that I kind of suggest or suggest is that these are kind of static structures. In fact, they're not static structures. So one of the things we'll look at is a couple of different ways that these structures are more dynamic. One is that there are some pKa's of some of the amino groups here, and so that there's some protonation and deprotonation, the bases after all. And then secondly is that we also have some keto-enol tautomers. So let's first of all look at the pKa's, and so let's see this way. Just put it up here. So of cytosine, the pKa, this lone pair, if it gets acidic enough, can accept a proton. So the pKa of this is 4.2. Similarly, this could come off. The pKa of that is 9.9. So then normal physiological pH, this is the structure that we see, but we have to kind of recognize that we start moving away from a little bit from that physiological pH. We started going basic, this would start to deprotonate, this would actually start to protonate in there. So again, just understanding that these structures are one of several potential structures depending upon the pH. They're the most physiologically relevant structure that we saw, but we have to recognize that there is the potential. Particularly start manipulating DNA and then start changing the pH, then you're going to start changing the structures. Okay, the other thing is a keto-enol tautomerism. And this is, let's see, which one will, let's deal with cytosine first here. I'm going to redraw this. Actually, this is keto-enol and amine, imine. Imine tautomer. This, for example, I'll give you is amine tautomer here. When we have that going on, that remember that this isn't a resonance structure, but basically we can have we can move this hydrogen over here so that we have this structure.
The carbon has too many bonds on it.
Right here, right, got it. You know, when you get into the, if you haven't already, when you get into the double helix book, the Watson double helix book, you'll see where they describe wrestling with it, trying to figure out, okay, what's the appropriate structure to use in building their models? You know, both in terms of the protonation state of the different molecules, as also in the tautomeric state as well. So that's imine tautomerism, and let's go over to look at thymine. Here we have the Keto-Enol tautomerism. Methyl group here, that's the structure I gave you before, and then we can basically do a similar kind of thing, in which now we're going back and forth. So this is thymine. All right. So what it basically is, again, why we're going over this is to recognize is that while you can go Google the structure of thymine, that's the structure that gives you the exact dynamic structure. And that structure is going to depend upon the pH, and it's also going to have this Keto-Enol tautomerism going on. And so, the structures are really dynamic. It's not as simple as just one straightforward structure. All right. Now let's go ahead and move on and start talking about the pyrimidines, the purines. One of the things I like to do to remember this is that the purines are the bigger molecules, and the smaller name purine is the bigger molecule, the bicyclic molecule. The bigger name pyrimidine is actually the smaller molecule from my opinion. I don't know if that's next are the purines. And a purine has this structure. we're going to have a functionalized purine. We're talking about the bases. Particularly, first we'll talk about adenine. Now this, we've got that nitrogen there. We've got a pKa of around 3.5. When it gets acidic enough, that'll protonate. Now, the reason pointing this out because we basically here we have an H-bond acceptor. Here we have an H-bond donor. Next one is swarming. This pK is 2.1. This pKa is 9.2. And I'm not going to draw through everything again, but just to point out, you can basically, here's an opportunity here for keto-enol tautomerism. And then there's a opportunity here for amine, imine conglomerates. All right. What we're doing is we're building a nucleotide. A nucleotide is a base plus a sugar plus phosphate. And so far we've talked about the base, the 5 major bases. I should mention, before moving on, because I won't get into any other bases, but there are other bases up there. Also, in a lot of organisms, the bases are further functionalized and derivatized. So in point of fact, sort of this is the dogma. Here's these 5 bases. If you actually go to a lot of organisms and cleave the nucleotides and cleave off the bases and do structure analysis, you'll find a lot of extra methylations in there, prenolations, all sorts of different things coming in on the functional group, particularly when you start looking at RNA molecules and tRNA molecules. But nonetheless, these are the major ones that are out there, and particularly for the 4, the adenine, cytosine, thymine, and guanine that are in DNA, these are the pretty standard structures that are in there. Now, what I want to do now is to start building the rest of the molecule and adding the sugar. When we add the sugar, I haven't been pointing this out, but basically in our serines down at this nitrogen here, and in our pyrimidines down at this nitrogen down here at the bottom. Now the sugars that we add to, there are 2 potential sugars. One is ribose, the other is deoxyribose. Now we haven't gotten into the sugars yet, so I won't go into a lot of detail. Hopefully you might remember a little bit of something from your organic chemistry. Our sugar basically is a little bit of organizational structure here. So this is B, sugars. A with the bases, B is the sugars. So ribose has this structure. The numbering of this is carbon number 1, this is carbon number 2, this is carbon number 3, 4, and 5. This is ribose. This is the sugar that's used in RNA. For DNA, the sugar lacks this hydroxyl group at that 2 position. So it becomes deoxyribose. That's in DNA. Now, so how much of the sugar chemistry you remember for organics, but remember the sugar, this is the anomeric carbon, and the hydroxyl group can either go up or it goes down. When it goes up, what's it called? Remember alpha, beta?
Axiom.
Yeah, when it goes down, it's alpha. When it goes up, it's beta. Alpha, when it goes down, it's alpha. Alpha looks like a fish and it's swimming below the water. That's what it looks like. I don't know. There's a lot of different ways to remember that. But this is beta. So this is in the beta conformation. that when we link our base, it's a beta glycosidic bond. So when we're linked to a base, let's see, I'll link it to, I'll keep it easy to try to think. This is a beta glycosidic bond. It could be any of those bases I just drew cytosine diseases. Now this whole molecule here, consisting of base plus sugar, is known as a nucleoside with an S, and that's a base plus a sugar. And the nucleosides have specific names depending upon the base. And the sugar. And so, for example, this one here is, instead of, let's see, the base is cytosine, the nucleoside, the base plus sugar, is cytidine. Okay, and next time we'll review those guys. Oh, let's go ahead. We've got a minute. Let me go ahead. So the names are we have cytosine is the base. The nucleoside name is cytidine. If, let's see, thymine is the base, it's thymidine. Uracil is the base, uridine. And let's see, if adenine is the base, it's adenosine. And if guanine is the base, then it's guanosine. All right. We'll leave you there for right now. Make sure you get that homework finished up. We'll come back in. We'll wrap up nucleotides and then start linking together to make nucleic acid. I'll also be talking a little bit on Friday about some of the biological role of the nucleotide, independent from the role of